Thank you for watching Knowledge Academy. Okay, in this video, we will be talking about a very important concept in Calc 3 or in general calculus called extrema of a function of one variable or two variable. But before we start this topic, let's take a look what is extrema means. So every scenario, every scenario in our life can be representing a equation. And if the scenario is very complicated, equations are not enough, you want to creating a surface, right? Just like you have your college grades, you're taking some course and your grade is basically going up and up and up. But the thing is that if you're working hard, your grade is going up. But maybe you have another activity or hobby like you playing sports. So what's happened if you paying too much or consuming too much time in study, you're not playing. So basically you not playing sports and your hobby is lacking, your passion is lacking, that's going to go down, right? If I combine these two, maybe you ended up in something, maybe a neutral line, right? Or maybe you prioritize your study and then not try to be emphasized too much on this on the sports, but you're still playing a little bit, so the line is going to be more somewhere here. So bottom line is that every scenario like that, you have to creating these kind of lines and function. My goal is that I want to find out what is the max you can do something or what is the minimum you can do something. How much study you can study. And maybe your threshold is you have only 24 hours every day, right? You have only 24 hours every day. That is your max time that you can study. Or you can do 24 hours every day, just you can play. So that's the max time for your sports. If you want to bring something in between based on your current preference, maybe you say education is more important, so you dedicate it up to 18 hours of education and 6 hours of sports, and you come up the total is 24 hours. So now your function, the shape of the function is changed. So what I'm going to do, I'm going to be making these scenarios and talk about the graphical representation. Right? These scenarios, I'm going to be making the graphical representation of these scenarios and finding what are those. So let's take a look. This is basically a curve is given. You can see a curve, right? And this curve going to be representing some situation. I don't know what is that, but I'm not interested to know about what are the details. All I can say, based on this curve, I can give you how much max you can do and how much min you can do based on this curve. Somebody decided this curve based on their priorities, their preference, their limitations, their criteria of selection. So every question is given to you. They probably just give you the curve or surface. Okay. If you see from the top, if you go from here, probably your eyes is here. You see this whole thing. You don't see this kind of inclination, the highs and lows of this curve. All you can see a rectangular pattern. Right? If you see from the top, you're gonna see something look like this. And what are those? These are the boundaries. The one I just example I gave you 24 hours. Right? So these are my boundaries. But if you remember, these boundaries can also say this is my domain. Right? Domain is my boundaries. Technically, we learned about domain, and domains are the boundary. So my allocation of resources like my time, my money, my whatever, material cannot go beyond these boundaries. So I'm going to be stay there. Maybe I'm finding some point here and I'm going to go up and see what is there. Oh, this is my point. If I'm going to make this point, I say this is the maximum I can do for the study, and then I go back and see where I'm located. I'm going to be located maybe somewhere here. Now, this is a 2D representation. This is a 2D representation. So I can call this is a curve. But things are not as simple. We have to completely go into the 3D. So that's the same surface you can see in 3D. So really, you can see you can go highs and lows, and then again highs and then lows, and then, you know, or maybe you can say the water you know, pouring the water on this point. You know, you're pouring the water here. The water is going to come here, come down, then come up, flow, and then come down, then come up, and then come flow. So the bottom line is that water cannot go more than this height, and water cannot go below than this height. Maybe water after come here and then fall off. But after fall off, he says, wait, I'm not going to look here because this is my boundaries. I cannot go beyond my boundaries, right? This is my boundaries. I don't consider anything beyond my boundaries. Okay. You can see another way of this shape like this. All right. So now take a look on these maxima and minima, and we call it extrema. So the word extrema come from extreme, right? When you say extremes, extremes could be one way or the other, positive or negative. So maybe call max, x is also extreme, the minimum is also extreme. So somebody living in a very extreme conditions, it could be maybe he's a very rich person living in a very lavish life, or maybe he's a very poor person living in a very bad life. These both are extreme of life, right? The situation they are living. So let's talk about these things in a more prospective way. Okay. So what I'm going to do when I'm talking about these extremes, extrema or minima, maxima, I'm going to draw this maybe curve. This curve is going to come down, come up, come down, right? So if you look at one thing is that I have a bunch of points here. This point, this point, this point. Right? These are the point where the curve making turns, right? But these are the point where the curve making turns. And when the curve making turns either this way or this way, these are the points where I'm interested to know about. So I'm going to call them A, E, C, D, E, F. Maybe here it is G. The point is that I have to watch few things here. Number one is this is my minimum value. This is also my minimum value. This is also my minimum value. This is also my minimum value. Same thing, this is my max value. This is my max value. This is my max value. There is no doubt or confusion about it. Whatever is highest is high, whatever lowest is low. Right? So I have two things going on. One is the most highest point in this curve look like is the maximum highest point in this curve look like is B. D and E are not the highest one. If I'm going to draw the line, it's going to pass here. So D and E may be not the highest one. So what I'm going to do, I'm going to call them maybe. I'm going to distribute the max into call. There's two kind of max point. One is called the max of the max, called absolute max. Right? Absolute max. The other one called relative max. Right? Absolute max, relative max, and the absolute max is the max of the max, and relative max is the max, but there is another max after that. So basically, this is a tip, but not the highest one in the system. Okay. There is another name, we call it global max and then local max. Local means locally here is max, but if you move here, you can find another one. If you move here, you find another one. So that's a local max. Same thing, I have a minimum. Let's take a look on the minimum. So we have in minimum, we have A, C, G, E, but look like everything except this. This is my absolute min or minimum. The whole word is minimum, but we use a shortcut called min. The other A, G, F, they are not the absolute, but they are relative. So I'm going to call absolute min and then relative min. And then I also call global min. This is called local min. In this case, I'm going to call this absolute max is point B. Here I have a point D, E. Here I have an absolute min is A. Maybe C. Right? My point C is the absolute min, and A, G, E are my relative min. Okay. Let's moving forward. There is an implication. No, there is an implication applicable only for absolute point. But nobody talked about to me about two more things. Why not this point is a max? Why not this point is a max? They are max, right? Or maybe the curve is coming here down. Maybe this point is min, right? So another thing we're learning here, we're going to make some changes in our system or definition. We're going to say that we're going to treat absolute a little bit different. Okay, let's treat absolute a little bit different. And I'm going to say the absolute point can be endpoint, can be endpoints of the curve. However, relative points cannot include endpoints of the curve. So it means when I'm talking about endpoints, endpoints are this one point and this point. I should include them when I talk about the absolute, because they should be the part of the absolute. And minimum point, a relative point, could not be except including those points. So what does that mean? I'm going to change a little bit definition and adding two more points here. And I'm going to call maybe this point called K. This point also called L. K and L. I'm going to say which one is higher. Okay, here. So what I'm going to do now, I'm going to change my points definition and says, well, in this curve, the maximum point, maximum highest point, technically speaking, is L. K is lower than L. So I'm going to erase this guy, my maximum point, and change it to L. Right? I'm going to change it to L. That's my point. Since this is an L point is changed, then B becomes what? B becomes a local maximum point. So I'm going to include in here. B becomes a local or relative. But the question is that what about the K? Why the K is not going here? Because remember, K is the endpoint. This is also endpoint of the curve. Endpoints only considered for relative for absolute definition termination. They cannot be considered for relative. So really, K point is nothing here. Cannot be relative, and they cannot be absolute because L is the absolute one. So I'm going to ignore the K. Okay. I hope that explains the difference between local max and local min. Let's take a look at another one. So if I'm going to make a curve like this, you know, and here I'm going to be making, this is my point of consideration. Why? Because the curve is changing the direction. Whenever the curve is changing the direction, that is my concern, and I have to look. So these are my this point. These are the point where the curve go from bottom down, right, towards the bottom. Is going from up and then going down, right? So these are the highs. These are my highs. I'm going to make my lows. Lows mean the curve is going down and then bumping up, then going down and bumping up, and these are the points. Okay. Then I also want to be considered two more points, different color, maybe green color. This point, this point. These are my end. Yeah. Let's try to rerun this whole definition again one more time and see what we got. What is on the x-axis? This x-axis I have my domain. Remember, I just showed you something like this, and then if you see from the top, it's going to look like a if you see from the top, it's going to look like this white color rectangle, which is my domain. So really, what we're doing, we're seeing everything from here. So this line is my this line, and this curve is look like this curve. Pretty much is what we have. So I'm going to be writing here. F has a relative maxima, right? This is my function. F has relative maxima, at C1, C2, C3. What are the C1, C2, C3? At, when I say at, I should give the value at domain. So I'm going to draw up here, dot, dot, dot. Then I'm going to go here, dot, dot, dot. Then go here. I'm going to make this line extend a little bit. And I'm going to call these points C1, C2, C3. C1, C2, C3. And these are the consideration points. So this is my range. Right now I'm looking into this range because this is my box. You can see the red color box is my range. I'm looking into this. Same thing here. F has a point of maxima, relative maxima at C1, C2, and C3. F has a local maximum. Local maxima at where? Since local and relative are same, so I'm going to say the same thing. Let's go back to the second part of this right? So this is one done. I'm going to write another one. F has a relative minimum at somewhere on domain. So I have to do the domain point. So I'm going to come here and then say this point, maybe changing colors. You know, since we are don't have much colors left, maybe do this color. I'm going to call C3, C4, and this one is C5. And I make this little area. Okay. So local maxima, local minima, relative minima is at C3, C4, and C5. Same thing, F has a local minima at C4 and C5. Right. I'm going to write here one more thing. Endpoints of the domain do not count for relative max or min. This is what we talk, right? So here I have two options. I have to look into that. I need to find out where is the absolutes. We That's a question we throw at. So I'm going to say here for a minute, just stay here. So this is my max. Yeah, it's an endpoint, but that's not the highest one. Is not the curve is not look like this. If that's the case, then this is the highest point. But the end point is not the highest one because I have another one, and this is the high of the high. Nobody higher than that. So these 2 points I am considering for my low for my absolute, but they are not the highest one. So what I'm going to do, I'm going to write here. I'm right here at this curve. F has an absolute maximum at C1. I can also write here F has a global maxima or max at C1. Okay, here is according to definition. Now let's talk about the absolute minimum. The absolute minimum, I have a bunch of options. I can look at this point, this point, this point. Okay. Looks like this point is not out of option because there's a lower here and then lower there. If I talk about the absolute, I could consider this one. Absolute, I can consider this one. I could not consider for relative, I cannot consider this point. So at this point, I'm going to say F has a, I need to give some point. So I'm going to come here and say this point may be C6. And I can also say this is the end point. This is also an end point. We are not just using because it's not the max or min. in either ways. So I'm going to say is F has an absolute min at C6, and F has a global min at C6. But just so you know, we just make a assumption. If I'm going to make this line, yeah, look like it's pretty much same, but if we make it, maybe a little bit this line. So point out here. So now you know that it's very clear that this is a lowest of all lows. This is the lowest of all lows. All right, let's take a look at another example about this. Determine the absolute extremas. So it covered both of minimum and maximum of the function. Extrema is a covered of both minimum and maximum of the function on the indicated region. On the indicated region, and the region is given something like this. The function is given in the mathematically, and that's my function. Look like is a surface, and the range is given, which can tell me the domain x and y such that x less than equal to 1, y less than equal to 1 or 2, y is 2x. If I want to draw this thing here, so this is my x-axis and my y-axis. If I'm going to draw, so it's going to be x is 1, 1, 2, y. So I'm going to be drawing something look like, and it can go to both ways. So I'm going to go to here, here, here. This point is 1 minus 2. This point is 1 comma 2. This point is minus 1, 2. This point is minus 1, minus 2. And really, this is my domain. Right? This is my domain. So I'm going to check all the points. Before than that, I want to find a critical point, a local point. So I don't know, maybe this is a, you know, maybe this is a, like a, this shape. So you see the domain like this guy is what you're seeing on the screen right now, but how does it look like? So I want this point. And maybe it's just like, maybe this point. Maybe it's a dome shape, upside down. So if I see again here, you just see this square, and this is what you're seeing here. Same thing, if you just go here, you're only seeing again a rectangle shape, which is domain. So you're seeing only this, but you don't know how this shape looks like. That's what I need to find out. Okay. And when you find out, you need to find out this is a minimum or maximum, this is another point, that's another point, that's another point. These are the points we need to be determined in this case. Okay. Since all these informations are not given, so what I'm going to check, I'm going to check all the points. I can check these. I can check here, 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 here. I can check this line. I can check this line. I can check that line. I can check that line. So I'm going to check all three, 4 side and 4 corner. Then I'm going to also checking here what this guy is basically look like, a dome shape somewhere here, or maybe like a dome up this shape. So I need to find out what's going on here at this point. Okay. Now I need to be taking solution and finding those point called critical point. Okay. So I'm going to take the partial derivative with respect to x for this function. So it's going to be y, right? Y equals to 0. If I say with respect to x, everything will be y equals to 0. So that is my first point. And if I say with respect to y for this function, if I take the partial derivative with respect to y, it's going to be x plus 2y. So we already find y equals to 0 from the first point. If I take this substitute over here, my x becomes 0, 2. So I say my critical point. My critical point in this function is 0, 0. Critical point means something happening in 0, 0. It's either a function is doing this, and that is my 0, 0, right? So if I draw this thing, this is 0, 0. Either my function is touching like this, or my function touching like this. Something is happening here. It's changing the direction. So I need to know the value of this point. So 0, 0 is my coordinate basically. Just like I have one coordinate here, minus 1, 2, 1, 2, minus 1, minus 2, minus 1, 1, minus 2. The fifth coordinate is 0, 0. My fifth coordinate is 0, 0. I need to check 0, 0.2. So really I need to check 4, 4, 8, and 9 locations. 9 locations. Number 1, this point, this point, this point, this point. I want to check this side, this side, this side, this side. And the last one with 9th one, I want to check the 0, 0 point, what function is doing. Okay, let's jumping and doing real quick. So I'm going to check my function at f1, 2. I substitute the value is going to be 1, 2, plus 2 square, and the answer is 6. So function value is 6 at 1, 2, which is right here. So value of the function is 6 here. Then I'm going to check at other value 1 minus 2, which is other side, is going to be 1 minus 2 plus minus 2 square, and the answer would be 6, 2, 4, 2. Answer is 2. The other point I'm going to be checking is minus 1, 2, which is this point, and it's going to be minus 1, 2 plus 2 square, and the answer would be 2 again. The last corner I'm going to be checking, corner, right? I'm going to be checking the corner. It's going to be minus 1 minus 2 plus minus 2 square, and the answer would be 6. All right, I got all 4 corners done. Let me check f0, 0. The answer is 0. So really the value of the function at 0, 0 is 0. It just happened. It's a coincidence. It's not always happening. Now what I'm going to do, I'm going to be checking this blue side, which is this side and this side. I'm going to be checking these two sides, and I'm going to write here along path x equals to 1. And I'm going to do the same path. See, this is x equals to 1 path, and this is x equals to minus 1 path. So I'm going to be checking both. So let's do it along x equals to 1. So I'm going to say z equals to, my function equals to y plus y squared, because of the x value is 1. So if I substitute the x value 1 in the function, my function is y plus y squared. Okay. I'm going to take the derivative of z, which is a function derivative with respect to y. So it's going to be 1 plus 2y equal to 0. From here, I can find the value of y equals to minus So I find x equals to 1 and then y equals to minus half, maybe somewhere here. So look like minus 1 over 2. So it should be somewhere here. Something happening here. I don't know what is happening. So this along this curve should be here, right? At this point, my value of x is 1 and y is minus half at this point. And what I need to be determined. So what I'm going to do is raise this point a little. And I'm going to be just checking the function at this point. So check the function at this point, 1 comma minus half. And the answer would be 1 plus minus half squared. And if you solve, the answer would be 1 over 4 with minus sign. And I check this point, which is 1 comma minus half. Ready? I'm going to check along path x equals to minus 1. X equals to minus 1. So I'm going to take my z function, the function, and then substitute x equals to minus 1. The function is going to be look like this, y plus y squared. And if I take the derivative, it's going to be minus 1 plus 2y equals to 0. And then I find the value from here is y equals to half, just half. Okay, I take these half and then 1, and then somewhere here, maybe here, right? This is my value of this point, pretty much minus 1 and half. And I'm going to be evaluating the function. So let's substituting the value here maybe. It's going to be minus 1. Right? My function should be minus 1 and half. So the function is minus 1 half plus half squared. If I do this one, it's going to be minus 1 minus half plus 1 over 4, and it's going to be answer will be minus 1 over 4. So really I'm going to be just grabbing the highlight, make sure I just picked up this one. This is my that's my function value. This is my function value. Okay, these are all for my function values. I just want to be no. So this is my function value, 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 this is my function value. So far I complete 5 and 2, 7 points. I need to do to check more. So let's do and then check the 2 which is along this line and this line, or I can say along the path. Right? That's a better terminology we use, along the path. Since I have a limited space, I can just make separation. And I'm going to be checking along path y equals to 2 and along y equals to minus 2. Right? So these two red color lines, I just draw it over there. Those are the lines. So z function equals to 2x plus 4 when you substitute the value of 2. Z prime when you take the derivative is going to be 2. So really there is no x left. It means cannot proceed. So this is not, is undetermined point, right? I cannot consider point. This is not a critical point. It means the function at this point is not doing this, is not doing that. I don't know what it's doing. Maybe going straight, or maybe this line, or maybe this line. I have no idea. So this is a critical, not a critical point. So I can not proceed. I'm going to say is not a critical point. Critical point means really when they make a turn. Let's check the other one. Along this one is equals to 2x minus 2x plus 4, and if I take the derivative, it's going to be minus 2, so not equal to 0. Minus 2 never be equal to 0. What we do, we just take the derivative and make it equals to 0, and then find the variable value. So minus 2, there is no x or y left, so it cannot be a critical point. So really, or I can say not a critical point or inflection. There's a word called inflection. Inflection means when the curve start turning like this and this. So this is a turn when they make that inflect. When they make a turn, they call inflection. So there is no inflection point here, really. Yeah. Okay, I think I did pretty much all my math. So I can mark here. So I got, yeah, I'm gonna make these blue. Yeah. So let's go here. So these 2 points are not in consideration, or the path is not consideration. So the red color path, I make it here, pink one, is not even a point. Let's talk about the max and min. Max and min, right? So I'm gonna, maybe I can change the color. I can say max point are green and min points are this one. So max one is I got 6. I got 6 look like max, and 2 and 2 look like min, but there is another min, minus 4, 1 over 4, minus 1 over 4. So these are look like my min point, because my 2 and 2 is not the max, so 2 and 2 is not the min. So if I just look at the extreme point, these are look like the extreme point. Unfortunately, or fortunately, which way you are thinking about, in this curve or this surface, we have 2 max point and 2 min point because they are equal. So if this is 6, other one is 6, I cannot ignore one or the other. I have to pick both. But if one is 6, one is 5, I'm going to pick the 6 one. Is a minus 1 over 4, minus 1 over 4, I have to pick one. Or I have to pick both because right now both are equal. But if one is the least, let's suppose one is minus 3 over 4 divided by minus 1 over 4. I'm going to pick minus 3 over 4 because that's a bigger number, right? But now let's take a look. How can I draw this function? So I'm going to be drawing, which is the harder one. So from the top is look like this. And if you want to see this, maybe function is going to be look like pretty much, you know, if you rotate this function a little bit, it's going to be look into 3D. In the 3D is going to be look like this. I hope I can draw this one. It's basically you're taking a piece of cardboard. I'm going to erase this guy. Okay, this is my shape of like a piece of paper, and then you fold it look like this. And now just try to put the point. So the green points are look like 6, 6, probably, 2 points maybe look like this point and this point of the 6. Right, that's the function value. And if you want to go here, probably this point is 6 is 1, 2. So this point, this corner look like 6 somewhere maybe. And the other one is minus 1, minus 2. So the other point. So these two are look like this point and this point are the max point. So I can draw these 2 points, alternative points are the max point. Min points look like is not on the corner, it's on the line. See, these points are on the line or on the path. So what I'm going to do, I'm going to go along the path. Which path? This path? No. This path? No, because these are already undetermined. So I'm going to look at the other path, the one I use, so x equals to 1 and x equals to minus 1. So x equals to 1, x equals to minus 1, the value is 1.5. So maybe somewhere here and here. So these are my two minimum points. Okay, the coordinate of this point is probably 1, 2. Right, the coordinate of this point is minus 1, minus 2, and the coordinate of this point is 1, minus 1, minus half, sorry, and the coordinate of this point is 1 and sorry, minus 1 and half. The values are this. These are the coordinates, the values are this one. Minus 1 over 4, minus 1 over 4, and these 2 points, the value is 6, 6, right? So I'm going to write here maybe with white color all the values. This one is 6, this one is 6, this one is minus 1 over 4, this one is minus 1 over 4. Okay, and I'm going to call it, the last thing I'm going to add here, absolute maxima or absolute mean value. These are the 2 points I'm going to be adding. These are the 2 points I'm going to be adding. Absolute maxima is 6 and absolute minima is minus 1 over 4. Right? This is what they ask in the function or in the question. So extrema function of two variables is nothing but is just checking the extreme values within inside the domain. Okay, extreme values. But the point is we have a condition extreme inside the given domain. And I told you in the video that if you have a function like this, write this function. So let's talk about this function and just review what we discussed earlier. So in this function, we do have this point, which is the highest point A. Then we have this point, which is highest point, second highest point B, and then third highest point C. Then we have lowest side, on the lower side, we have this point, which is called D. Then we have E, and we have F. We also have two endpoints. One endpoint is here, which we can call it G maybe, and maybe here we can call it K. We have two kind of extreme values, and those extrema, so let's put it this, extreme value means extrema. Extrema means it could be minimum, it could be maximum, it could be minimum. Okay. Further, in this maximum, they also have two category of maximum. One is called local, the other one called global. These locals also called relative, and other one called absolute. Absolute means absolute of the whole function. Okay. Now we're going to be doing the same thing for minimum. We have local minimum, which is also called relative minimum. We also have global minimum, which is also called absolute. Okay. Now the condition for this local, right? For local condition is that it could not consider the endpoints. So K and G are not including in the relative consideration. So we cannot consider G point and K point for anything relative. So these cannot be considered for G and K points. Okay. Now, if I'm talking about the global, I'm going to first of all let's talk about the global, which is easy. So I'm going to see global means the maximum of the maximum. Okay, the maximum of the maximum. So I'm going to see the local here. The maximum of the maximum point is what point? K is the maximum. Nothing is more bigger than or higher than K. How do I know? I just make a line, it passes under A. A is a little bit lower. I see the difference and I can figure it out. The K point is the highest point. So maybe I can say this is A absolute or global, right? Global maxima. Same thing, point G is the global minimum. Or I can call it absolute, or global minimum. Now the thing is, let's go back to the other two types, which is called relative, which is most of the time. Relatives are we have to deal most of the time, right? Because function can go to many highs, many lows, right? This function goes to many highs, and I have to deal all the highs again and again and again. And same thing with the lows. I have to deal with all these lows, all the lows over another one, and all these lows consider as a relative low, relative minimum. So here, A, B, C are my relative maxima, right? So I'm going to be writing here, maybe I can write here, my relative maxima here is G. So this guy is G. This should be K. So this is the global minima is G, and the other one would be K. This one should be K. Now let's talk about the relative maxima. The relative maxima is A, B, C, and the relative minima is D and E and F. Now one more thing is that I'm going to just make more changes in my function to look into that. I did not talk about the F point for local. Since I talk about too much about maxima, which is easy, I need to know that G and F. G and F, I have to consider, is that my local or is that my global? So if I do here, if I make a line, G is here, F is here, pretty much lows and the low. So I'm going to say, you know what? This point should be the lowest point than G. So I should not be considered G is the minimum. I should be considered F is a minimum. Now the point is that F is not the end point. F naught is the end point. F is in the middle of the function, right? You can continue the function afterward. You can continue the function. You can continue on both sides. So F, and the fact is that F could be the lowest of all low. So we should be saying minimum is global. Should not be G. Should not be G. It should be F. But a few minutes ago, I just told you endpoints are not considered for relative, but they should consider for absolute. It does not mean they are the only one considered for absolute. So you're going to be considered this, right? And I'm going to coming here and stop here. In this scenario, what's happened? I have the lowest low, and then I have this point. This point is actually nothing, really nothing, because this point is not the lowest one. This is the lowest one. So this is my global point. And this could be also, you can say this is your global, and this is also relative, right? So every global could be also a relative point for that function, but not necessary that every global is a relative or local. Okay, so I'm putting the F points here. This is my F point, and I'm going to also making this F point with green color F, right? So I have the local. F is my local minima, and I also have my global minima. G point really have no value. G point is not. G point is in the middle. So G point really have no consideration in this function. I mean, it's a point. You can evaluate the value of the function at this point. If I give you coordinate of G, maybe I can say 1, 2. You take these 1, 2 points and substitute in the function. You will probably find the values. Okay. Now, After this thing, we have another problem start. We have another problem start. Some points are called, here I can call saddle point, right? Saddle means, you know, the horseback saddle. The saddle shape is like a donut which is squeezed from the bottom, in the middle. You know, there is a donut you can squeeze in the middle. How's going to be look like? It's going to be look like probably like this. Now this point I'm going to call it saddle point, but this is a 3D point. This is a 3D point, and I'm going to show you how this point looks like. The problem is the saddle point is you are not sure. You are not sure after this point you're going to go up or down, right? What I say, this is a confused point. I'm confused at this point, or unsure, or it could be either going up like that. What I'm saying in simple words, after this point, my function could be going up or down. Okay, I'm going to show you this saddle point. So we have a problem with the saddle point. I want to check every point, like this point, 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 and that point, and check, make sure they are not saddle. Because if there is a saddle point, I cannot do anything. I mean, saddle points is unsure. I cannot tell you, if you give me a saddle point, I'm not going to tell you it's a minimum or maximum because I'm not sure. Okay. So let's talk about the saddle point for a minute. And then we're going to talk about how do we deal with that. So first thing, we need to find out what is a saddle point if we're not sure, and how we're going to be dealing with the saddle point. Okay. So two things going on. Perfect. In this view, you can see these are my local minima, local minima. This is my local maxima, local maxima. Why I'm saying local? Because I'm not sure if the function is going to go here and then come back here. So I just call it local maxima, local minima. Maybe these are the absolute maxima or absolute minimum, but I'm pretty sure this is minimum. The only thing I have to figure it out if it's absolute or relative, but I'm pretty sure this is minimum. I'm pretty sure this is a maximum. I have no confusion about it. But look at this point. This is a saddle point. And what I'm saying saddle point is this function can be going this way, right? So look like this is a maximum point. If the function going this way, this is a max point. But if I look on the other side, you know, from the blue shade, I'm gonna go from this axis, is gonna come down here and then touching and coming. So I'm confused. This point is either this point or this point. I'm not sure. So look like I have two curves going on in this point. If I'm gonna draw on the curve, one curve is gonna be coming like this and touching, passing this, and another curve of maybe green color curve is passing here like this. So the green one saying this is a minimum point. The red one saying this is a maximum point. So you know what? I don't want to deal with this. I'm going to ignore this point. Ignore. So if you give me a point P or anything X, Y, which is maybe this point, X, Y values, and you give me a point, I'm just making up some numbers, 2 and 5. If I substitute this value and if I figure it out, this point is a saddle point, I'm going to ignore this point. I says, I'm sorry, I cannot tell you. It's not a maximum, it's not minimum. I cannot tell you. Okay. So the first thing we're going to call some critical point yields saddle point. Which neither relative maxima nor relative minimum. Another thing we're learning here is it's using the word relative, right? Relative means Saddle point never be ending here. I mean, saddle point or not. You cannot say that the curve is coming here and end. Can you check this point is saddle point? No, it's not. Saddle point always have to be continuity on this point. So means saddle always the issue for relative, not the absolute. Okay, saddle point is always the issue for relative, not the absolute. So what I'm going to do, I'm going to deal with this saddle point and finding some alternative. And I'm going to be using a test. I'm going to do my test to check if point is a saddle point. And that test should be a shortcut, right? So the shortcut of this doing it is called second partial test. Right? This is a test telling me if my point is a saddle point or not. And in order to do the second partial test, I'm going to bring it here. Second partial test theorem is this. This theorem is look pretty complicated, but don't worry about it. What I'm going to be doing, I'm going to make it simple. In order to do this test, like a second partial test, I need to find discriminant. Right? I need to find a discriminant. Right? This is the word discrimination, right? The word discrimination we hear a lot of times nowadays. But this discrimination, actually the word came from the pretty much same point. This math actually developed the word discrimination, and then we use that word in different kind of context nowadays. But discrimination means you try to discriminate either here or there, or differentiate between the two things, just like its verbal meanings too. Discrimination means discriminate. But in math, definitely you're not discriminating with things. We are just discriminating if it's a relative minima or maxima, or it's a saddle point. Simple. So how this thing look like? You're gonna take the function. Let's suppose the function is giving x squared plus 2x squared plus 2xy plus 3 equals to 0. You're gonna call this function xy function. And I'm going to take the first derivative with respect to x. Then I'm going to take the second derivative with respect to y. Then I'm going to take the second derivative with respect to x. Then I'm going to take the second derivative with respect to y. Then I'm going to take the first derivative and take the first derivative with respect to y. Okay, when I have all these things like this thing, this thing, this thing, I'm going to write this times this. I'm going to multiply these two, right? And then minus. Then I'm going to take this guy, which is fxy, and take a square root. And if this term called d, I'm going to call this term d, which is my discriminant. Okay, this term called d, which is my discriminant. And if the d is bigger than 0, d is bigger than 0, then I'm going to proceed. D always bigger than 0 if you have real roots. Real roots means real roots, right? X equals to plus minus 3. This is a real roots. If x equals to minus 1, that's an imaginary number. So I cannot proceed this one. This is the imaginary number. It's not even exist. So discriminant test is telling me if my roots are real. Okay. So if d is less than 0, d is bigger than 0, it means my roots are real. If d is less than 0, it means my roots are imaginary, right? And if the roots are imaginary, it means this is a saddle point. Okay, this is a saddle point. I should not be proceeding this condition. I says I couldn't tell you. Sorry, at this point I couldn't tell you if it's a maxima or minima or relative maxima or relative minima. If the d or discriminant equals to 0, it means this point is not even exist, or I cannot conclude anything. We call it inconclusive. The test is inconclusive. We cannot apply this test. So this test is not applicable when discriminant equals to 0. Okay. So I have really 4 conditions. Number 1, if d is bigger than 0 and fxx is bigger than 0, then it's a relative minimum. It means This is a case like function like this. If d is bigger than 0 and f(x) is bigger than less than 0, it means it's a relative maximum, which is this guy. So this point I'm talking about. This one is saddle point. I already talked to you. Is just like this point. You know, the point is actually look like either is this way or that way. So you confused. So you don't want to be dealing with this. So you don't have to tell anything. You just say this is a saddle point. If d is equals to 0, then you say this test is inconclusive. I cannot even deal with this. I cannot even tell you what is that. Okay. So I'm going to take some examples and go over with them. So we'll take a look at some examples for second derivative or second partial test and go over with that. Find the relative extrema of a function, which is this. Okay, this is a function is given. I need to go and find a solution. First thing first, I need to find out the first derivative, right? And we need to find critical points. Since points are not given, I don't know which point I'm going to be finding, but I know that every time this function looks like this. I don't know which point I'm looking, but I knew that if I'm going to look into this, let's suppose this point, I knew that if I'm taking the derivative of this function by finding a tangent line, right? I'm finding a tangent line, and I can tell you this tangent line, either this function is this or this function is, you know, at this, right? If I find the tangent point, I'm going to make these tangents and this tangent. So I find the tangent, but look like this is a maximum point or local maximum. This is a local minimum, and this is a local. So what I'm going to do, I need to find the local critical points, or these points where I can make the tangent. So begin to find the critical points. Since the critical points are not given, begin by finding the critical point. Okay, and how do I find the critical point? I'm going to take my function and take with respect to x. So really I'm going to take my function and says df equals d over dx. That's what I'm doing right now. Okay, and I'm going to take my function and take the the derivative with respect to x, and that one will be minus 3x squared for this, and it's going to be plus 4y, and everything else will be equals to 0. So I'm going to write here 0, everything will be 0. The second thing what we're going to do, we're going to be finding the same thing we're going to do with y. Take the derivative with respect to y, and it's going to be 4x minus 4y. And the rest of the things becomes 0, so I'm just going to write in 0. Okay. And now what I'm going to do, I'm going to take these two and then writing like this. 3x squared plus 4y equals to 0. I'm going to make it equal to 0, right? I'm going to make it equal to 0 because my derivative of any point should be equals to 0, because derivative is a slope. Remember, the derivative dy over dx is a slope, is m slope. And if tangent looks like this, the slope should be equal to 0. So I'm substituting it to 0. Same thing I'm going to do it here. I'm going to say 4x minus 4y should be equal to 0. And that's what I'm going to be using to finding my critical points. Okay. So what I'm going to do, maybe I can just equate these two equations. Look like both equations have 4y. Maybe I add them, and they, they remove the y term and only x term left over. So if I'm substituting, right, x equals to y, I would say that x equals to y. If I substitute, I'm going to be finding some critical point, and my critical point by solving these equation number 1 and 2, I find my x equals to y equals to 0 and y equals to x equals to, I find 2 points. Really, this is just what it means. I find 2 points, 0 and 4 over 3. So that's my solution for these 2 points. And what I'm going to do, I need to apply the second derivative test. I'm going to erase all of these because I have need a space. I'm going to say second. Sometimes you write second like this. Derivative test. Okay. You can call second derivative test. Some books or contexts call just a derivative test. And here I need this. For second derivative test, I need second derivative. So my second derivative of equation number, this equation, I'm going to say minus 6x. My second derivative with respect to y for this function equals to minus 4, just minus 4, extra will be gone. And my xy, the first derivative with respect to x, then taking the second derivative with respect to y, equal to, and this is a function, so if I take with respect to x, with respect to y, is going to be just 4. Okay, I got all my things in a box, so I need this guy, I need this guy, I need this guy, and I need the derivative, which is my lowercase d's. Some books using uppercase d, and I'm going to substitute 0, 0, right? That's my first critical point. So my first critical point is, after solving them, is going to be 0, 0, right? And the other critical point is this. So I'm going to check this point and this point. I'm going to check point number 1, which I'm checking right now, 0, 0. And then I'm going to be substituting 0, 0, second derivative. And then I'm going to say is my first derivative with respect to x and second derivative with respect to y, and substitute the critical point and take the square root. So if I'm going to substitute here, x value 0 is going to be 0 times minus 4 minus, this is going to be 0, 0, and then it's going to be minus 4. Sorry, 4 minus, and then 4 squared. So if I solve this one, my answer would be 0 minus 16. Okay, so really my d coming up minus 16, which is definitely smaller than 0. It means I have real root. Okay, let me go back to the previous slide. So my d is equals to minus 16. So I'm going to check minus 16, minus 16, and I am here. Look like d, this guy, maybe, right? And if my d is smaller than 0, I don't have to do much, check anything else. I can just simply come and say this is my saddle point. If d is bigger than 0, then I have a real roots. If d is smaller than 0, which is I have right now, minus 16, I don't have to check the roots because my roots would be imaginary. Okay, so I'm going to say is, from this test, we conclude here. If I want to put 1, so 0, 0 is my, we don't have any function. If I substitute 0, 0 in the function, my function, the original function, which is here, if I substitute this like 0, 0 here, it's going to give me 0 plus 0 minus 0 plus 1. So everything will be 1. So if I substitute 0, 0 in the function, my function value is 1. So I'm going to say 0, 0, 1 is a saddle point. Remember, I have a function like this, and I'm substituting the values like 0, 0 into the function, which is this one, right? This is equation, and I got the value which is equal to 1, right? If I'm going to check other point, maybe this point, I should have another set of points, and if I'm going to check, it's going to give me some other numbers. So what I'm going to do, I'm going to check the other point, maybe here. Since I'm going to be finished on the same slide, so let me erase some of the stuff. Maybe I don't want this. And I'm going to make some room and making a line so we're not confused. I'm going to check the other point, by the way. Now I'm checking this point, 4 over 3, 4 over 3. So I'm going to substitute by checking 4 over 3, 4 over 3. I'm going to checking this point. So D equals to fxx 4 over 3, 4 over 3, then fyy 4 over 3, 4 over 3 minus function xy 4 over 3, 4 over 3 y value, and then I'm going to take the square of this. Okay, so this one will be, if I say 4 over 3 here, 4 over 3 is going to be minus 8 after simplifying. And this one is just minus 4. There is no x and y value, so really it doesn't matter. I'm going to just type here minus 4. And then minus, right? And this value is 4 to the power square. So really if I solve, it's going to be minus plus, and it's going to be 1632. 32 minus 16, right? And if I solve further, so I'm going to get my 16 answer for the D. Okay, now D is 16 means D is bigger than 0. D is bigger than 0 means I have real roots. So I have to go back to my test and check. Okay, I have to go and check my test. Here is my test. This test says D is bigger than 0. If D is bigger than 0, number 1 and number 2, I have to check XX, XX. What's going on with that? So let's go and check if fxx or f with second partial derivative with second order, if it's bigger than 0 and less than 0. If it's bigger than 0, it's going to be minimum. And if it's less than 0, it's going to be maximum. Okay, so let me just check my points. I know that D is bigger than 0 in my case here. So I'm going to check my fxx, this guy, and substitute the value. If I substitute the value, I already substituted, and I knew that D is bigger than 0, and second thing is fxx equals to, I substitute the 4 over 3, 4 over 3. This point is, this guy is equals to minus 8, which is less than 0. If less than 0, I think is a maximum. If less than 0 means, you go back to the test, but the way I remember, if it's less than 0 means maximum, if bigger than 0 is minimum. So less than 0 means is a maximum. So I'm going to go ahead and say here, we conclude f has a relative is a key here, relative maximum at 4 over 3, 4 over 3, right? If we want, we can substitute the value in 4 over 3, 4 over 3 in the function, and it definitely gave us some value of the function, which is the value of the function. We don't have to tell the value of the function, to be honest, but you can find the value of the function if you have to. Okay. Let me take another example. Whenever I say extrema, I cover or should be looking both minimum and maximum value. Okay, and the function is given this. Sometimes the value of these critical points are given. Sometimes the critical points are not given. And most of the time it's not given. So we need to find out these critical points. And it's pretty simple. You take this function and then we can apply by checking the critical point. We're going to check the critical point. We're going to check gx and gy. Right? It means I'm going to take the derivative with respect to x and y and substitute equal to 0 to find the value. So it's going to be 2x minus 1. And if I try, and should be equal to 0, I'm going to make it substitute equal to 0 to finding the value of x. From here, if I say it's going to be x equal to 1. Right? I'm going to take the 2 divided by 0 is going to be 0, and if I bring the 1 on the other side, it will be plus 1. So I'm going to get one value for x. I'm going to do the same for y. It's going to be 2y minus 3, and this one is equals to 0. I make it equate to 0. From here, I can say y equals to 3. Right? So I need to find the value of my critical point is if I substitute this critical point 1 and 3 in the equation on the function, so 1 I'm going to say is 1 minus 1 squared plus 3 minus 3 squared equals to my function, which is my gxy function, and everything is gxy should be equals to 0. Okay, so this is my 0. So maybe I can say, I can write like this critical point, I can also like 1 3 0. The last one is my function value, right? So you can write like this way too. But anyway, I already got my critical point, so let's check it, right? So I need applying second partial test, second derivative partial test. One thing I told you, second partial test is a shortcut to find the saddle point. So it's not only helping me to find the saddle point, it's also helping me to find the relative extrema, right? Relative extrema. If you remember on a previous lecture, I gave you a very long example where I checked the lines on the side and the points. It was a very long example. That's basically a manual method or like an actual method to checking the relative or absolute maximum. Okay, that point covered everything, relative and absolute both. But in that example, the example I did in the previous lecture, I checked for absolute point. The absolute point could not be done with second partial test. Absolute point has to be done through manual work. Second partial test can only be very helpful and usable for relative extrema values. So I can check extrema values, plus I can also check saddle point. So really, partial derivative test is good for relative extrema plus partial saddle point. You can check everything in one shot. So here I need this guy, right? And this one, if I take the second derivative of this function, 2x minus 1, the answer would be just 2. Then I check the y for xy, the second partial derivative with respect to y, and the answer would be just 2 again, right? The answer would be 2 again. Then I'm going to check this guy because I need xy, and this one is going to give me 0. If I take here with respect to y, it's going to be get 0. Okay, I'm going to substitute these values in my second partial derivative test and finding the, the values is going to be d equals to 2 minus 0 squared. Right? Really, I don't need to substitute this critical point value. And to be honest, at this point, critical point have no meanings really, because critical points are just a point. I haven't used it. I don't need them in this case because my function does not even have any variable left when I do my second partial derivatives. So 2 times 2 minus 0 squared is going to be 4. So my discriminant or d comes out to be 4. So d bigger than 0. Now I'm going to be checking my second thing, which is my fxx. And this one maybe need my critical point, right? This one maybe need my critical point. So if I'm looking my critical point over here, gxx equals to just 2, right? Gxx equals to 2. Again, I did not use my critical point. I did not use my critical point. And I'm going to say here, my conditions right now here is gxx equals to 2 and gxx is bigger than 0. So if I say it's bigger than 0, mean it should be a minimum value, right? Bigger than 0, minimum, less than 0 is maximum. It should be other way around, but the way I remember them, if it's bigger than 0, it should be minimum. If it's less than 0, it should be maximum. So I'm going to check this one. So we, based on our test, we conclude function is at local or relative minimum, or I can write just minimum, which is look like sounds much better, at 1, 3, and if I substitute the value, the answer should be 0. Okay, so these are my 2 points. I can just write 1, 3 should be fine. We don't need to include this 0 point, but this is my relative minimum. Okay, maybe look another example. Find the local extrema of a given function, and the function is like this. G xy 5 minus x minus 6 squared minus y plus 2 squared less than equals to 5. This time function is giving a little bit different. So what you're going to do, we're going to quickly check. Since we have a limited time, we're going to be using some drag step. So I'm going to checking my point. So gx equals to minus 2, x minus 6 equals to 0. From here, x equals to 6. Gy, I'm going to check, is going to be equals to minus 2y plus 2 equals to 0, and y equals to minus 2. Then I'm going to substitute for finding gxx, and gxx here is just minus 2. Gyy equals to minus 2 as well. And gxy equals to 0. When I take gx and with respect to y, nothing is left, so I have three things. So I got this, I got this, I got this. I'm ready to substitute in my discriminant equation or second test. I'm going to say here -2 -2 -0, and this one equals to 4, which is bigger than 0. Okay, at the critical point means the point when the curve have called inflection, right? This word is also going to come some of the problem called in point of inflection. They try to trick you, but doesn't means to disturb and confuse. Inflection means really is a point when the curve is doing this or this, inflect. So this is my pretty much this is my critical point. So critical point also used a word called inflection point. Okay. So at a critical point, which critical point? The one we just evaluated, 6 comma -2, d is bigger than 0, and g x is less than 0. If I substitute here is -2, less than 0. So if it's less than 0, should be maximum, right? Right? We have relative maximum. And if I want the function, I can also write 6 comma -2. And if I substitute 6 comma -2 in the function, so it got 6, 0, and I think everything becomes 0 on the left side, but the function left over is 5, right? This is a given here, so I'm going to just write here 5. So really this is a function value. This is my function value at the given point, which is we just found 6 comma -2. Thank you for watching Knowledge Academy. Please subscribe my channel.